Okay, students, please put your attendance in the command window. We will directly go to the class. In the last class, we have discussed Euler's formula. Are you remembering that crippling formula for critical load? That is, PCR is equal to pi square EI divided by LE square. That's the equation or Euler's equation. So, before going to the problems, we will just go to understand what is equilibrium of column. Whenever we are studying something that is equilibrium condition, we have three equilibrium for a column. First one is stable equilibrium, second one is neutral equilibrium, and third one is unstable equilibrium. നിങ്ങൾക്ക് നോട്ട് എടുക്കാം. Please write it as there are three equilibrium. Equilibrium of column എന്നുള്ളത് heading. So subheading ആയിട്ട് എഴുതുക. Equilibrium of column heading. താഴെ എഴുതുക. There are three types of equilibrium. There are three types of equilibrium. There are three types of equilibrium, namely stable, neutral, and unstable equilibrium. Namely stable, neutral, and unstable equilibrium. Namely stable, neutral, and unstable equilibrium. And the subject idea stable equilibrium. Stable equilibrium. Heading is the stable equilibrium. It's very common equilibrium actually. Whenever we are applying a force, the position will be changed, and when the force is removed, the element will become towards the original position. This is common equilibrium that is known as stable equilibrium. A stable equilibrium is one in which bodies in static equilibrium on being displaced slightly returns to its original position. That is, when we are applying a force, the body will undergo a deformation, and when we replace that rod or return that rod, the body will regain its original position. That is stable equilibrium. I can show you a figure. Here, when we are giving a force P to the column will displace slightly. But when the load P, compressive load P is removed, the body, that column will return to its original position. This is an example of static or stable equilibrium. And you can have a figure here. By drawing a figure like this, you can understand what is stable equilibrium. Whenever we displace, here there is a boundary A and boundary B and a ball A. When this ball is moved towards this point, after removing our force or removing hand, the body will be returned to its original position. That is here. When body is moving to this position, that body will return to its original position. This is known as stable equilibrium. Whenever you are giving a force, the body will undergo a displacement, and when you remove that load, the body will regain its original position. Such equilibrium is known as stable equilibrium. Heading a stable equilibrium. A stable equilibrium is a stable equilibrium is a stable equilibrium is one in which a one in which a one in which a body in static equilibrium one in which a body in static equilibrium a body in static equilibrium a body in static equilibrium on being displaced slightly 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 return to its original position, returns to its original position, returns to its original position, returns to its original position, and continue to remain in equilibrium, 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 and continue to remain in equilibrium. എഴുതി കഴിഞ്ഞു വിചാരിക്കുന്നു. This is stable equilibrium. From here, can you guess what is neutral equilibrium? Obviously, unstable equilibrium will be the opposite of this one. When applying a force, there will be a displacement. When returning to removal of that force, that will not come to original position, that may go to somewhere else. That is unstable. So neutral position is where neutral equilibrium is one with body is in equilibrium, on being displaced does not return to original position, but its position stops and resume in equilibrium state at its new position. അതായത് whenever we are applying a load, the body will undergo a displacement, and when we are removing that load, the body will remain in such position, in same position, and that will be its new equilibrium position. This is known as neutral equilibrium. In the first case, stable equilibrium, when we are applying a force that's displaced and removing, that will come to original position. Here, when we are applying a force that will displace, and after removing force, that will not come back, but that position itself become new equilibrium position. That is known as neutral equilibrium. We can show a figure. When applying the load, the body will displace, and even after removal of load, the body will be in the same position. This is an example of neutral equilibrium. Here A is the ball, B is the surface, that will be a horizontal surface. When we are moving this to this point, the body will be in new equilibrium position. That will not come back to original position. This is neutral equilibrium. So write the heading neutral equilibrium. Neutral equilibrium. A neutral equilibrium, a neutral equilibrium, a neutral equilibrium is one in which is one in which is one in which is one in which a body is in equilibrium. A body is in equilibrium. A body is in equilibrium, comma, on being displaced, on being displaced, on being displaced, on being displaced, does not return to its original position. On being displaced, does not return to its original position. On being displaced, does not return to its original position, comma, but its motion stops and resume, but its motion stops and resume, but its motion, sorry, but its motion stops and resumes, but its motion stops and resumes, but its motion stops and resumes its equilibrium state. In equilibrium state at its new position. In its equilibrium state at its new position. At its new position. Please draw the figure. കഴിഞ്ഞതിന്റെ ഫിഗർ വരച്ചില്ല തോന്നുന്നല്ല. സെയിം ഫിഗർ ആണ്, ആകെയുള്ള വ്യത്യാസം എയും ബിയും വരുന്നത് മാത്രം. Please note down the figure. Please note the figure. Please do it fastly. We are not having much time. Can I change the slide? Can I change the slide? Hope you have drawn the figure. Neutral equilibrium. So finally, the last equilibrium condition is unstable equilibrium. Here, whenever we are giving a force or we giving a slight displacement, the system disturbs. But when we are not we're removing the force or displacement, it will goes to another equilibrium. It will not return to original position. It will not resume in that position, but goes to another position. That is an unstable equilibrium, in one in which a body is in equilibrium on being slightly disturbed, moves away from its equilibrium position and loses its state of equilibrium. That is unstable equilibrium. You can see a figure here. A is the ball and B is the surface. When ball is slightly moved towards right and remove the displacement, the ball will go downward. That is away from the equilibrium position. This is an example of unstable equilibrium. When we are considering a column with A and B, one end is hinged, both ends are hinged, and applying a force, there is a chance of going towards another equilibrium, that is unstable equilibrium. This is an example of unstable equilibrium. Just compare stable, neutral, and unstable equilibrium. In the stable equilibrium, when we are displacing something, that will regain to initial position after removal of the force. And neutral displacement, when we are displacing the element, that will not go to the original position, but that will remain as in the position where we remove the displacement. That is neutral position for neutral equilibrium. And third one is unstable equilibrium. When we are when a body in equilibrium is slightly disturbed, that will undergo another motion or that will lose its state of equilibrium. That is unstable equilibrium. Please write down. Heading is unstable equilibrium. Unstable equilibrium. An unstable equilibrium. An unstable equilibrium. An unstable equilibrium. An unstable equilibrium is one in which is one in which is one in which is one in which a body in equilibrium, a body in equilibrium, a body in equilibrium, a body in equilibrium, a body in equilibrium on being slightly disturbed, on being slightly disturbed, on being slightly disturbed, on being slightly disturbed, moves away from its equilibrium position, 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 and loses its state of equilibrium, and loses its state of equilibrium, and loses its state of equilibrium, and loses its state of equilibrium. Just a figure വരച്ചിരിക്കുക. Please draw the figure. Okay, hope you have drawn this one. I will go to a problem. This is the more three equilibrium conditions for a column, that is stable, neutral, and unstable equilibrium. So after that we are going to solve a problem. For that I am taking a problem as given here. Write the problem. Euler's crippling load കാണാനുള്ള problem ആണ്. So write the problem. Find the Euler's crippler load. Find the Euler's crippling 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 load for a hollow cylinder steel. 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 Column of 38 mm external diameter. Column of 38 mm external diameter and 2.5 mm thick. 38 mm external diameter and 2.5 mm thick. Take length of the column as 2.3 meter. Take length of the column as 2.3 meter and hinge at both ends. Hinge at both ends. And hinge at both ends. Hinge at both ends. Take Young's modulus ES. Take Young's modulus ES. Take Young's modulus ES 205 kilonewton per mm square. 205 kilonewton per mm square. 205 kilonewton per mm square. This is our problem. We need to find crippling load, and for finding crippling load, we have an equation, Euler's equation, that is, you need to write PCR equal to pi square EI divided by LE square. That's given to us. For that, we need to Give the available things. Given things are outside diameter is given, hollow cylinder the outside diameter is 38 mm. If this is the hollow cylinder, this inside diameter is Ci, outside diameter that will be, one minute, outside diameter will be, this diameter will be Do. That is given as smallest Do ആണ്. So Do is given as 38 mm. Okay, and thickness also given, that is 2.5 mm. So from here to here, the total distance is 38, and we have 2.5 here and 2.5 here. Then you can find di by minusing do minus 2 into t. അല്ലേ? നിങ്ങൾക്ക് ടോട്ടൽ ഡിസ്റ്റൻസ് 38 ആണെന്ന് അറിയാം. തിക്നെസ് 2.5 വീഡിയോ ഉണ്ട്, താഴെയും തിക്നെസ് ഉണ്ടാവും 2.5. So when minusing 2t from do, we can find inside diameter. That's why I have drawn this one. You will be confused. So given data are outside diameter, thickness, length smallness, and length L is equal to 2.3 meter. Actually, that's not suffix, that's 2.3 meter. And to find PCR, that crippling load, we need to write Euler's equation. As we know that Euler's equation is L square EI divided by L E square. There is a mistake, not L square, that is L E square. For all the equation, you can use it as L E square. L E square. So here the problem given as both ends are hinge. So that you can find LE for the both end hinge condition. For a both end hinge condition, L is or LE is given as small l, that is 2.3. And I you need to find out. You have an equation for finding moment of inertia, that is pi by 64 do raised to 4 minus di raised to 4 for a hollow cylinder. As we have already known that do is equal to 38, we need to find di. For that, use this relation, that is di is equal to do minus 2 into t. If you have any doubt, you can ask now, because it's an important equation. That is, do is given, di is equal to do minus 2 into t. From this figure itself, you can understand this thing. That is 38 minus 2 into 2.5, or 38 minus 5, that will be 33 mm. So do is 38, di is 33. After substituting these values in the moment of inertia equation, you can find out I as this value. Please write down this equation, that is given data should be written. After that, equation for PCR, that crippling load should be written. After that, effective length for a both and hence case should be written. Moment of inertia should be written. And since do is given, you need to find di. For that, you can use this relation. Please tell me once you write complete this page. Also use calculator to find value of I. Do and di are known to you. No need to convert it into meter. Just do all the calculation in mm, so that effective length also should be converted into mm. If this is converted into mm, that will become 2300. That is 1 minute. This will become 2300 mm. 2300 mm. Can I change the slide? Have you completed this one? Anand,
Yes, sir.
okay, I am changing the slide. If you are not completed, please inform me. After doing the calculation, I have found the value like this. Please check this one because I have copied from someone somewhere else. So if you are substituting and finding any other answer, there may be chance of error here. So tell me, what is the value of moment of inertia? 5 by 64 into t raised to 4, that is to raised to 4, that is 38 raised to 4, and 33 raised to 4.
Sir, 44140.112.
Okay, no issue.
അല്ല
No
സെയിം തന്നെ
issue.
ഇതന്നെ വരും.
Okay, no issue. You have to write as what you have got. There will be slight variation if you are substituting pi as 3.14 and someone may directly substitute pi. So there will be small variation. Hope the answer is correct for I. After that, you have to find what is PCR directly. If you are directly substituting the value, PCR will become pi square into Young's modulus is in which is the unit that should be checked. That's in kilonewton per mm square. When we are converting kilonewton to Newton, that will become 205 into 10 raised to 3 Newton per mm square. So Young's modulus will be 205 into 10 raised to 3 into I is find out as this one. If you are getting 4 for 110, you have to substitute that value. And we have length, effective length as 2300, that is 2300 mm. So that should be written here. And after calculation, they have got value as 16850 Newton. Check this value also.
ആ ഇത് വരുന്നുണ്ട്.
Okay. So the answer is crippling load is 16,856 Newton, or converting it into kilonewton, that will become 16.86 or 85. That's whatever you want, you can write. That is the final answer for crippling load. It's a very simple question. Sometimes the same question asks for 4 marks. So you need to study this one because it's an important problem. And while doing this one, you will get the answer. And I have another problem for you. Just check. It may ask in your question paper. I will not give the answer for this one. Just I will mention the steps. So write down the question. That is compare the strength of solid circular column. Compare the strength of solid circular column. Compare the strength of solid circular column. Solid circular column of diameter 200 mm, of diameter 200 mm, and hollow circular column of same cross-sectional area, and hollow circular column of same cross-sectional area and thickness 30 mm and thickness 30 mm and thickness 30 mm. Other parameters are same for the section. Other parameters are same for the sections. Other parameters are same for the sections. I will just give you a clue. You need to write this one. This is a tutorial work. You have to complete this one by yourself. So I will give some clues. Here, Young's modulus will be same. Just equate the crippling load. Then you can find out the ratio. Which crippling load will be more, which crippling load will be less. That is the question. For that, we have an equation for crippling load as pi square EI divided by LE square. Pi is common for hollow and solid. E is common for both, but I is different. Moment of inertia is different for solid shaft and hollow shaft. But LE, length, the effective length also will be same. There is no change for effective length, only diameter is changing. So you need to find out the ratio of high solid to high hollow. That is moment of inertia of solid to hollow. Then that will be directly giving the buckling strength of solid column and hollow column. So this equation is pi by 64 d raised to 4. This equation will be pi by 64 do raised to 4 minus di raised to 4. And we have di and do is here. Thickness is given. So di will be do minus 2t. നമ്മൾ ലാസ്റ്റ് കേസ് ചെയ്ത പോലെ തന്നെ. Okay. After that you have to write the equation, and pi by 64 is common for both. So ratio, the strength ratio will be d raised to 4 minus do raised to 4 minus di raised to 4. We have d as 200 mm, but we have no idea about do and di. But we have another condition as given in the question, that area is common for both. That is, solid shaft in the area is equal to hollow shaft in the area. So pi by 64, solid shaft in the diameter is 200, square is equal to pi by 4, do raised to 4 minus di raised to 4. Then you have to substitute di as do minus, sorry, di as do minus 2t, and after that, after solving, you will get do and di. And after putting this value in the ratio of buckling strength, you will get the hollow shaft or solid shaft, which is the stronger one. I will not give the steps, but you have to do the calculation and find out the answer. And when you are coming to the college, I think Monday onwards you will have offline classes. If that, you need to show me this tutorial. Okay, it's very important work. You have to do yourself. Please put your attendance if anyone pending. And if you have any doubt regarding that substitution, you can ask me now. First of all, you need to write the crippling equation for solid shaft, crippling equation for hollow shaft. After that, some common terms will be there that can be eliminated. That is, pi will be common. In the question paper, the all other parameters are same given. So E will be common. Effective length will be common. But moment of inertia cannot be common because solid shaft and hollow shaft having different moment of inertia. After taking the ratio of moment of inertia, there will be D as well as DO and DL. And comparing these things, and we have a given condition that area is constant, that is pi d square by 4 is equal to pi d square by 4. That is pi do square minus di square all divided by 4. After dividing all these terms, you will get the relation for do, and di. And after solving the equation, you will get the values for the both, and you can find the ratio of moment of inertia directly substituting the values of t, do, and dx. From that, the final answer will be hollow shaft will be the stronger one, not solid shaft. Hope you are understanding. If anyone pending to give the attendance, please type your attendance in the command window. The attendees are 3, 5, 9, 14, and 15. Is there anyone available? 3, 5, 9, 14, and 15. That is Adarsh Preman, Alan K. Sudeep Krishna, Muhammad Said Ashraf, Nihal Abdul Nasir.
സർ ജെയിന് കമന്റ് ഇടണല്ലോ.
ഓൻ്റെ നമ്പർ മാറിപ്പോയി. ഓൻ 13 ഇട്ടാന്ന് തോന്നുന്നു.
അപ്പോ 13 ആബ്സെന്റ് ആണോ? ഷെറിൻ ഉണ്ടോ?
ഷെറിനുണ്ട്, സെയിനുണ്ട്.
ഓക്കെ.